First, I guess we have a speaker from RIKEN and a speaker from Fujitsu. First, we have Keiji Yamamoto. He received his PhD in Information Science Technology from University of Tokyo, Japan in 2010. He's now a researcher of Operations Computer Technology Division at RIKEN. RIKEN's K computer belongs to the highest caliber of supercomputers in the world. He's working on a stable operation of a supercomputer. His research interests include system software, such as job scheduler and file systems for supercomputers. After Keiji will be Shinji Sumimoto. Dr. Sumimoto, he's a senior architect in the software development division of Next Generation Technical Computing Unit at Fujitsu Limited. He's in charge of technical development and software, especially highly scalable communication, large-scale cluster file systems. His research interests are high-performance computing, system architectures, especially high-performance communication and large-scale computing architectures. Keiji, please, right this way.
Thank you for the introduction. I'm Keiji Yamamoto, and a researcher of computer science at RIKEN AICS. And RIKEN AICS have a supercomputer called K computer. K computer is the fastest supercomputer in Japan. Currently, is number 4 in the world. We operated the K computer about from 4 years ago. Many troubles of file system occurs due to large scale. Today, I'd like to talk about client eviction problem on large-scale raster-based file system. This is outline of my presentation. First, let me tell about overview of the K computer and I/O architecture of the K computer. And second, I'm going to explain eviction problem. And finally, I'm going to evaluate the elimination method of evictions. K computer consists of 82,000 computer nodes. One computer node consists of CPU, memory, and interconnect controller. CPU is SPARC 64 processors manufactured by Fujitsu. CPU has 8 cores. In the system board, 4 compute nodes are mounted. Whole system consists of more than 800 racks, and peak performance is 10 petaflops. This slide is I/O architecture of the K computer. K computer has 2 kinds of file systems. One is local file systems, and the other is global file systems. Both file systems is based on raster file system with several extensions. Local file system consists more than 2,000 OSSs for performance. Storage capacity is 11 petabytes. And global file system consists of 19 OSSs and for capacity and reliability. Capacity is 30 petabytes. I'd like to focus on eviction problem. When the client doesn't work properly, file server evict a client. For example, no response to requests from servers. Since the eviction costs I/O stalls on the client node, I/O accesses of running job on the node will fail. In many cases, the jobs affected by the evictions are aborted. In case of the K-computer, many evictions occur frequently and node utilization decreases seriously. On the K-computer, eviction is one of the most serious issues. This graph is number of evicted computed nodes. As you can see, K-computer consists of 80,000 nodes. As you can see, eviction occurs several times with all computed nodes. We had analyzed the eviction log. What we found is many of evictions were related with OSS failovers and system board maintenance. OSS failover is caused by hardware and software failover and scheduled maintenance. System board maintenance occurs by CPU, memory, interconnect failures. This graph is same graph as previous slide. We observed strong correlation between large-scale eviction and OSS failover. Blue bar is evictions with failover. Large-scale eviction occurs 57 times, and 52 times is evictions with failover. Next, I'd like to focus on evictions without failover. That is system board maintenance. Eviction occurs by lock acquisition and recovery of between clients in the job. When clients access the same file resource, creating a file under the job directory, parent directory is locked. Client A has lock. Now client B requests lock. Then lock manager collect locks from client A. When system board maintenance, client A is evicted since this access is an error. This slide is physical configuration as the previous slide. Interconnect network connection was cut by system board maintenance. Even interconnect path changes, the request isn't retransmitted. As a result, eviction occurs. We have eliminated eviction in two ways. One is system operation level. The another is improvement of file system level. We changed operation of maintenance of system board. At first, we had maintained the system board during another job running in the rack. After changing the operation of maintenance, we maintained the system board after stopping cabinet or stopping rack. This method eliminates evictions, but unavailable compute node increases to about 200 from 4 compute nodes. This graph shows the number of evicted computer nodes excluding failover. Middle of February, we changed operation of maintenance. As you can see the graph, eviction is eliminated after February. We improved the file system level. We fixed 2 issues. One of the problems is clients don't resend lock collection requests under some situation, and depletion of server thread resource to receive client reconnection in case of MDS or OSS overload. We added sequence to fix the situation and resend. And we prepared dedicated server thread resource. By the 2 fixes, eviction occurrence rate was reduced to 170 seconds. This is summary of my presentation. Thank you.
So questions after my talk. So next talk is metadata access reduction. And here's the outline of my talk. First, I introduce some file system usage in a user job in a computer. Then I talk about some file access issues on a local file system. And then I talk about metadata access distribution by Loopback file system and evaluation on the computer. So let's talk about my file system usage. And I talked maybe many times on the lag. So computer have a FEFS, and the goal is to realize world top plus capacity and performance. And it's based on the Rust file system with several extensions. And these extensions are now going to be contributed to the Rust community. So computer has 2 layers file system or file characteristics. One is a temporary and file structure file system for local, and the permanent shared file system for global. So by using the staging function, which transfers between local file system, global file system, that is controlled by a batch scheduler. So I talk about job execution and file system access on K computer. As Yamamoto-san said, K computer has a 82,000 computing nodes and that's connected by the local file system with 1 MDS and 2,500 OSSs. That provides maybe a 3.2 terabyte file read and 1.4 terabyte read. Right. So when user in login, so user provide 3 information. One is the staging file, number 1, and a program execution script and stage at files. After user submit the jobs, number 2, batch scheduler automatically transfers the file from global files, specified by the staging files, number 4, to the local file system. Then job has started, and computing nodes read and write to the local file system. And after the finishing jobs, local file system specified the file is a special staged files automatically transferred from local file system to global file system. That's almost automatically controlled by a batch scheduler. So I talk about file access issues on a local file system. So many talks and lag. So metadata access issues in local file system is very problem. There are 2 issues. One is creating a lot of files per MPI ranks at a time. For example, 1,000 per rank creation becomes 10 million files creation per job. And creating and deleting files takes several hours to finish and call through the MDS response. Second is execute binaries on shared driver, shared directory. And it becomes a consolidation access to the single MDS and OSS from several 10,000 nodes. It takes a long time to finish, and long time delay occurs on starting jobs. And here's a evaluation of the December 2013, a week evaluation of MDS load. The average of MDS CPU load is around 24%. However, server maximum is 100%, and maybe some of several hours are over 90%. That's true. So that's also a problem. So issues to solve and our goals. And first I talk about issues and to solve. One is about consolidation access to single MDS or OSTs on job execution. And second is violent fluctuations of MDS and OSS load depending on jobs. That's a problem. So we took our goals, and one is distributing and liberalizing metadata and data access. Second is providing a fast access performance per MPI rank. And here's our solution, metadata access diffusion by loopback file system. And this is maybe a figure around here. And this is providing a real local file system per rank by using loopback file system. And creating a loopback file and MKFS for ext2 and mounting it as a ext2 file system per MPI rank. And rank local data and execution binary are copied to rank local file system. So our job scheduler system software automatically manages and creating, mounting, and deleting in the rank local file system. So to do so, MDS load can be decreased to only one file creation and deletion per rank, and no fluctuation and no dependence per job types. It would make some constant load. And so let's comparison about the multiple MDS and loopback. So multiple MDS maybe a raster distributed namespace. It will be good for increasing metadata access performance on shared file system. And however, requiring additional hardware resource, MDS and MDT, so scalability limited to hardware resource. However, loopback file system, it is good for completely scalable metadata performance for rank local access and no additional hardware. However, as you know, unable to share along the other node and additional EX file system and loopback data overhead. So let's talk evaluation on the K computer. We evaluated them as 3 topics. One is the single node file access performance. Second, the total metadata access performance, and comparison of MDT CPU load before vs after. So first topics, single file access performance. And here's the result in the read-write performance by I/O zone. X-axis shows the bytes in the up to 1 gigabyte, and Y-axis shows megabyte per second. And blue line is the FEFS in the raster-based file system. Its write performance around 500 megabyte per second. However, loopback file system real ext2 file system on the memory, so 2 gigabyte per second, up to 128 megabyte file. And read percent also 3 gigabyte per second, and raster also 2 gigabyte per second for client cache. And second, total metadata access performance. And x-axis shows number of clients. That means also a number of nodes. And y-axis shows the operation per second. It's a log scale. And this pointed to create and delete performance. And for FEFS, the raster file system is constant MDS performance. It's around maybe a 21 kilo operation for deleting files. However, for a loopback file system, as you know, maybe it's completely scalable. For example, for 9,000 nodes, 453 million operations per second on 9,000 nodes. So it is completely scalable over 9,000 nodes. The average is created 26 kilobyte operation per node, and unlinked performance is 37 operation per node. And providing higher constant metadata access performance for each node. And third topic is MDS CPU load comparison, before and after. This is a very long time evaluation except maintenance time, through the maybe December 2013 to February, at the end of February 2015. And we introduced the Loopback file system. We have a large job and small job. And the first of 2014, we introduced a Loopback file system for large jobs. And that's after one. And then after two, small and large files. And here shows before, maybe average MDS load is around 25%. And after one, it decreased to 8%, and after two, reduced to 6%. And also, we have some shorter peak occurrence times per day, over 50% and 70%. And in the before, maybe 2 or 3 times per day, over 50%. And over 70% is maybe 1 times per maybe 2 days. However, by introducing a Loopback file system, it dramatically goes down and liberalized to the metadata performance. It's less than 1/30. So summary, I introduced some metadata access division by Loopback file system. And evaluation and also is very good. And this shows the introduction of Loopback file-based rank local file system is very effective on K-computer system, even if 1 MDS and 25 hundreds of OSS file system. That's all. Is there any questions?
So I have a question about the previous presentation. There was something said about Lustre not resending lock requests or something, which is definitely not true. So I wonder if there are more details available on that. And in addition, the server thread overload is supposedly handled by us reprioritizing certain kind of requests specifically to avoid that. And I know Fujitsu FEFS has some changes in Lustre, but hopefully they didn't break that. Or like, I'm interested in more details in like those like part 2 fixes that were mentioned.
Yes, yes. Maybe you're talking about eviction.
Yes.
We have fixed 2 issues. So Fujitsu talked about last summit in maybe length, maybe to fix, and maybe I will contribute to the maybe this year.
Right, but the thing is,
maybe one is maybe at some point client does not send to the server because of maybe a connection status. Second one is maybe he said an overload. So client sends maybe a callback. However, server does not have response because no thread is to reply. That's the problem. We have to fix.
Right. So supposedly Lustre already has ways to deal with that. So,
okay.
But that's why I was wondering, like, why re-implement something that's supposedly there? Like, what was broken in the previous attempt at doing that? And about your presentation, I think by concentrating on MDS load, which is also important, you are overlooking the very good benefit on the client side, because when you have a loopback file system, all your metadata operations stay local because it's a local file system in a way. And you, like when you use Lustre, you open a file, you must send an RPC. It's a synchronous RPC. It adds latency and stuff. You open or create a file in your local file system like that. There are no RPCs at all. At least nothing synchronous. So like you totally didn't dive into that, but I feel like you also should mention that it, like you could do hundreds of thousands of creates per second, if not more, on your nodes, which some people value, especially if they run benchmarks.
Thank you. Thank you.
I was curious for the loopback file system. How much memory was dedicated to that per node, and what impact that had on?
Maybe, in K computer, they are limited to maybe 1.6 gigabyte. Because maybe K computer nodes have 16 gigabyte. However, for computing, 90% of memory must be used. So maybe 1.6 gigabyte. So maybe however, maybe file cache are limited to maybe 500 megabyte. However, in the loopback file, you're using a loopback file system and Lustre based file cache, and also have a loopback cache. So there are two caches, so half of the cache are needed.
Okay, so about 10% of the system memory is dedicated to that. Okay, and did that have much of an impact on the users? I mean, there's a trade-off there between memory available per core, bandwidth, and versus Lustre.
Because our solution is a very small file and so many times created. That is okay. However, maybe you can show that maybe over the cache, the performance goes down.
Okay. Sounds good.
That's maybe a trade-off.
I guess I've got a question. So I was grateful to Fujitsu for their contributions in 2.7 for OST placement. I saw in your talk that you intend to contribute additional code. Can you give me a sense of when?
What?
Code contribution. Do you know when you'll be contributing that code?
Yes. Maybe we have presented them last lab, and maybe we are scheduled. Maybe we put them IV bonding. Maybe 2 or 3 months related. However, maybe we continue. So maybe eviction is also scheduled.
Okay.
Yes.
Great.
If we need some loopback some bugs, so if our community needs, we will contribute to the code.
That's wonderful. Thank you. I'd like to thank you both.